Hi everyone. Today we're going to talk about how to manage scaling while keeping costs under control. Challenge accepted. My name is Corey Wagehoft. I've been a lead engineer at Relativity for 3 years and recently joined our architecture group with a primary focus on our global Kubernetes platform. At Relativity, we make software to help users organize data, discover the truth, and act on it. Our platform is used by thousands of organizations around the world to manage large volumes of data and quickly identify key issues during litigation, internal investigations, and compliance operations with Relativity One. Relativity has over 180,000 users in 40 plus countries, from organizations including the US Department of Justice and more than 70 Fortune 100 companies. Today, here's the agenda of what we're going to talk about. So we're going to go over how Relativity operates Kubernetes, our scaling challenges at Relativity, and what have we learned. How do we control our costs and maximize our compute utilization and maybe profit? So at Relativity, we operate right now around 17 large Kubernetes clusters in 10 regions in Azure Public Cloud, with more regions coming next year. We also operate in Azure GovCloud as well. While I can't share our exact cloud costs, I can give you an idea of the scale we operate at today, which is why it's important to understand your costs. Our two largest costs in Azure are compute and storage. We currently operate around 6,000 VMs globally outside of Kubernetes, which over the next few years, we'll be moving everything into Kubernetes. So understanding our costs and understanding how to scale are very important to our organization. We also expect to be managing around 8 petabytes of customer data by just the end of 2020. And we expect that to grow significantly over the next few years. So there are two different ways most organizations typically manage Kubernetes with their organization. So let's talk about two patterns that are most common. You can either let engineering teams operate their own clusters with their own processes. This creates a fragmented approach for building images, deploying applications, and security concerns. This makes it difficult also for cross-organization collaboration, and this allows teams to, it allows teams to move at their own pace, which can be a benefit at times. Another approach is creating a standard platform as a service offering for engineering teams. This unified approach around building images, application deployments, security posture creates a very good unified approach. It's also very easy to have common documentation, patterns, and a great network effect for your engineering teams as they're transitioning into Kubernetes. This does, however, require dedicated resources to build and maintain this platform as a service. So a lot of the times you need to be prepared to work ahead of everyone and identify areas of concern before they occur. So at Relativity, we took the second approach. So we have a platform as a service internally for Kubernetes, and we decided this because we just don't have a lot of engineers with great experience in Kubernetes. So we figured if we build a very nice platform on Rails, giving them a solid approach and foundation, this would be a much more successful experience for us as we move so much of our core services and applications from traditional VMs into Kubernetes. So as you can see on this slide, from a high level, here's how our platform is kind of divided up in Kubernetes. The lowest level on the bottom is where we stack our core applications. Applications like where we handle Istio, Prometheus, Splunk, Prisma, our security product, as well as custom operators that our team develops. At the next layer up, we have typical application platforms or RESTful microservices. And with these will expand out and have more and more of them in the future. And on top of some of our application platforms, we use these to manage our batch workloads. So in a good example that I'll continue to talk about as we go along is we have a lot of analytics work with Relativity for our document analysis. So we run these as different batch jobs of different sizes, and their execution time can be anywhere from a few minutes to a few weeks on the really big ones. So having a unified approach is great for us, but it does present some challenges when we prefer to operate less clusters, but at a larger scale due to operational costs. So one of the first challenges we're going to talk about with scaling is the challenges with bin packing. So typically in Kubernetes, one of the primary benefits is being able to pack lots of workloads densely together on a common compute platform. However, you do have some difficulties as you grow. In our case, we have the two different challenges of balancing, small RESTful microservices and large batch workloads at the same time on the same compute platform. So, and with these, we have, most services might use just a few millicores and a few megabytes of memory, very small. But we have some that, all the way up to dozens of cores and hundreds of gigabytes of memory for one workload. So this presents some challenges for us on how we maximize our compute utilization. Things around like how many pods per node you're able to provision, and then selecting your node sizes and the amount of pods on those nodes. It's a constant iterative balance. And there's some other challenges along the way when you start to introduce auto-scaling. So let's talk about that. So with bin packing, you get that density, but for us, we have a very dynamic environment, so we need to scale up and down for our compute needs. But during these auto-scaling operations, our nodes will become unbalanced. So we'll have some nodes that are very underutilized and some nodes that are utilized just how we want them. But this underutilization can lead to significant unallocated costs. So first, let's talk about the default behavior for auto-scaling. So the Kubernetes cluster autoscaler, typically, by default, a node must be below 50% of available capacity to be eligible for scale down. Additionally, for us, a node must not contain a workload that can't be terminated. So such as our large running batch jobs, we have to make sure those must continue. So nodes can become unutilized when they can't scale down. And future pods may schedule to these underutilized nodes, but without a custom scheduler, you can't guarantee this. So it's a good idea to rebalance nodes over time. And you can do this with a Kubernetes community tool called Descheduler. This will occasionally cycle pods around to different node pools and nodes when they're able to. So if you have workloads that it might violate a pod disruption budget, or in our case, we have specific labels to make sure that this doesn't happen, the descheduler won't take effect on this. So it's very good to work with. So it will work well with workloads that are designed to handle rescheduling very easily. And another good way to reduce your unbalanced nodes and your utilization is through the use of several different types of node pools. So pick different VM sizes and types based on your workloads, so that for us, in our case, because our differences in size vary so wildly on Kubernetes pods, we operate many different sizes of node pools in both VM type and scaling capacity to meet these needs. Next, let's move on to some other scaling issues we've run into. We've run into quite a bit of storage throttling from time to time on Azure. So in Azure, each node has a default disk that is where the host operating system is attached to. These disks, however, do have IOPS limits, and we typically provision the largest SSD-backed disk we can for each node to maximize our IOPS availability. We assumed this would work for us, but we were terribly wrong. First, let's look at a couple of the things that actually write to the disk typically. So you're always going to have I/O throughput from the kubelet, your CNI, your Docker socket, which is writing to standard out or standard error from your container pods. And when we add in engineering teams that like to use the empty dir volume Kubernetes for scratch space, we started to run into big problems as we scaled up in our node density. So what blew up? Bad things happen when you exceed your storage throttling limits in Azure. The kubelet and CNI can fall into a bad state, which eventually turns a node into a zombie state. The API server is not getting updates from the kubelet, and the kubelet can't determine the pod's health, so the workload may fail, and it might not reschedule because the kubelet and the API server aren't accurately tracking the workload anymore. We also would sometimes experience mass pod evictions on a node. And by default, Kubernetes does not reschedule these pods. So we would have failures of large batch jobs that must be deleted manually to reset them. And unfortunately, that's not a great customer experience for us. This ruined nights and weekends for several of us for quite a while. So while using empty dir for scratch space to perform very small file operations, that's not bad. But when you find engineering teams storing hundreds of gigabytes and doing heavy I/O operations, this can quickly exceed your storage I/O throttling limits. And in Azure specifically, when you exceed these limits, they typically will throttle you very hard, and they will penalize you for continuing to exceed that threshold. To get yourself back under the limit, you have to drastically reduce your utilization to the point our nodes are we're not able to use them. So at that point, it costs us compute dollars, but we can't put any workloads there. So let's talk about how we're managing this in the short term and the long term. So for now, what we had to do to kind of like put out the fire a little bit was we reduced the number of pods per node to keep us well under that storage throttling limit, and to basically try to slow things down a little bit. We also are leveraging the node problem detector application from the Kubernetes community that can help identify node issues when they do occur in an automated way. And we paired it with a tool called Drano, which is another open source project that works directly with node problem detector to drain and cordon nodes that are in a bad state. So this will hopefully help us not have late nights getting paged in the middle of the night, things like that. And the auto remediation will help reduce this issue. Now, this is a short-term solution. This is a Band-Aid. Our longer-term solution is we're telling our application teams, and we're analyzing who's actually using these volumes the incorrect way, and working with them to move to a better storage solution, such as in Azure, they're managed disks, but more importantly, they're leveraging true persistent volumes and persistent volume claims. Now, to also encourage teams to not abuse the empty dir volume, we've actually also set default size limits. So this will reduce people from accidentally, if they even don't know that they're provisioning that much storage, or if they didn't know they're not supposed to. And furthermore, we're going to leverage Open Policy Agent to build a policy that will block deployments when someone does try to provision a large empty dir volume. We'll just simply block the deployment. So now that we've covered our scaling challenges, let's talk about cost management. So unallocated resources is a large source of waste in Kubernetes. You're paying X amount of dollars per hour for your compute, and you should be trying to use the absolute most of it. There's a careful dance, though, between performance, utilization, and cost for node pools in Kubernetes. Unless all of your workloads are pretty close in size, you should run node pools of different sizes and the amount of pods per node. This will increase your complexity, unfortunately, in determining the size of which VM you should be using for your node pool and how many pods you should allow per node. But this does have the benefit of ultimately reducing your unallocated resources. If you want an extra challenge, you can experiment with taints and tolerations to help direct workloads to the right node pools. Now, while you can do this with affinity or node selectors, I don't recommend targeting a specific VM size based on the name of the VM size. This will introduce challenges for engineering teams, because if you do need to change the underlying VM size, you have to communicate that with all the engineering teams. They have to make configuration updates, and accidents happen. People will miss the communication, and it just won't happen. So in our case, because we manage the Kubernetes platform for the engineering teams, a better idea and approach would be to use taints and tolerations, where we can direct workloads to different node pools based on your requirements. So you might, and we can change those VM types behind the scenes without you even needing to make a configuration change. This allows our engineering teams to focus much more on their work and not the inner workings of Kubernetes. After tackling unallocated resources, we can address the next question that will end up coming from your finance department. What is the compute cost of an individual customer? Identifying how much a tenant or customer costs on our non-Kubernetes infrastructure is fairly straightforward for us through just using Azure's billing tools. For example, a good example of where, to calculate costs, we would need to take a look at how much a single large analytics job costs to execute. But to determine this, it's a complex problem. You need to know what kind of Kubernetes node it was executed on, how much CPU and memory the job requested to execute, how long did the job take to run, how much did Azure charge us for that single node while it was running. So the complexity just continues to add up. You can see how this quickly becomes a big problem. And when you not only have to deal with batch workloads, you also have to worry about your other microservices and RESTful APIs. So a good way, the first step is to leverage label taxonomy. Using labels is great to not only classify like what version of your application is deployed or what date it was deployed, but also how to identify cost centers. You can add labels for what department this workload belongs to or team. You can add, non-sensitive customer information like a customer ID that's a GUID. Even after we do label everything, how do we make sense of all of this? Well, we looked at it as an approach you can either do build or buy. It's a common thing that most companies do out there when they're looking to solve a problem. Originally, we planned on building a solution ourselves in-house, hopefully using an open source framework as a starting place and then contributing back to the community. The data, though, that we need to work with, there's a lot of different data sources for where we get ultimately our billing for it. We would have to look at, what's the best way to integrate with Azure's billing data? What's the best way to get all of the metrics and things that we need out of Kubernetes? And how do we join that data together to get an accurate picture? Unfortunately, there was not a great open source project at the time for us to solve this. We would have loved to adopt something and contribute back to the community, but it wasn't available. So we looked at, building it completely from ourselves, homegrown solution. We calculated roughly it would take maybe one engineer full-time 1 year to complete. Obviously, you can parallelize a lot of this work, but this is an easy way to kind of, back of the napkin, figure out the cost for us just to give us an MVP. Now, one thing you should take into account when you're estimating things like this is you should be accounting for ongoing maintenance, end user support, feature requests, things like that. Depending on the size of your team, this may work. But if you need more investment and need to expand your team, it may make more sense to partner with a vendor. So, Harness to the rescue. There are several solutions, though, in the cloud cost space, and you should definitely evaluate what is out there and what works for you. But Harness happened to come to market just in time with continuous efficiency. So it made sense for us to expand our partnership with them for the needs we had. So we use continuous efficiency to get an idea of like cost per cluster, per namespace, and per customer. We can now easily get a full picture into our costs, and with an API available, we can extract this data and feed it into our existing reporting systems as well. A key takeaway from all of this is, today we're using Harness continuous efficiency in all of our public Kubernetes clusters. All of our engineering teams that use Kubernetes can see their cost and efficiency. The engineering teams are actually looking at this data now. They care about this. Previously, engineering teams didn't have this much insight into their overall costs. Now they do, and are proactively working to become much more efficient. Product managers are also working to establish budgets, forecasts based on this data from continuous efficiency. So to recap, today we covered, how does Relativity manage Kubernetes at scale? What kind of scaling challenges did we have? How are we solving these? We're looking at how do we manage our costs and get a good picture of what's going on there. And with that, I want to thank you for the time today. And I would say challenge completed. We took care of how to manage cost at scale. Thank you very much for your time, and have a great conference.